Hello, everybody. My name's Steve. Welcome back to American Steam Legacy. Right from the start of the steam era, the spoked wheel had become synonymous with the steam locomotive. The spoked wheel would often find its way onto piling and trailing trucks, and in some cases, even rolling stock. The spoked wheel was the ideal solution for the application. It was strong, relatively lightweight, and easy to manufacture. But since locomotive drive wheels are made from cast steel rather than being machined out of a solid blank, there were some issues that had to be taken into account. Specifically, the rate at which the wheel cools while it's still in the mold. The more massive parts of the wheel, such as the area around the axle and crankpin hubs, would cool more slowly than the rim and the ends of the spokes. The difference in cooling rates and the associated shrinkage of the casting would create stress concentrations, or weak spots, at the spoke ends and in the rim. And while these things are not beyond a measure of control, the need for frequent inspections while in service were essential. As locomotives became faster and drive wheels became larger, precise balancing became an ever-increasing requirement. The weight of the side and main rods had to be counterbalanced by adding weight to the opposite side of the wheel, and this was in addition to the weight of the crankpin hub. In the early 1930s, there were several attempts to basically reinvent the wheel. A drive wheel that was strong, lightweight, relatively easy to manufacture, and able to be precisely balanced while eliminating the issues with uneven cooling was the objective. These efforts resulted in the Baldwin disc, the box universal, and skull and wheel centers. We'll take a look at each one coming up next on American Steam Legacy. The Baldwin disc, the box Scullin, and universal wheel centers represent four similar approaches to the same problem. The problem being the shortcomings of cast spoked wheels. While the spoked wheel served the railroads well throughout the entire steam era, there were some inherent issues to the design and manufacture that came to light as drive wheels became larger and locomotives became faster. The first major issue was counterbalancing. With the crankpin and crankpin hub on one side of the wheel, with the additional weight of the main and side rods, sufficient weight had to be placed on the opposite side of the wheel and counterbalanced. Achieving precise balancing was a difficult proposition at best. One solution was to cast the counterbalance slightly oversized, then remove the required amount of weight by drilling holes in the backside of the casting. In the worst case scenario, there simply wasn't enough space on the opposite side of the wheel from the crankpin to place enough weight and counterbalance in the first place. The second issue arose while the wheel was still cooling in the mold. With some portions of the wheel being of significantly greater mass than others, the cooling rate of the steel varied. These temperature differentials caused stress concentrations in the spokes and rim that would lead to cracks developing while the wheel was in service. The third issue was the weight of the wheel itself. Heavier wheels are harder on the track than lighter ones, and as the wheels became more massive, this leads us back to the counterbalancing issues. The Boxbach wheel center was the first attempt at addressing these issues. A 1932 patent filed by A.C. Wittenberg shows the early variant of the Boxbach. While the Boxbach version that would see common use later in the 1930s and beyond would differ in appearance, the underlying rationale remained the same. Wittenberg addressed the issue of uniform cooling by making the wheel a series of thin-walled hollow sections. The hubs for the axle and crankpin contained the heaviest wall thickness for the required strength in that area, but the area surrounding the hubs was a thin-walled hollow section with the hollows extending through the spokes and the wheel rim. In fact, this is where the box gets its name. The box refers to the hollow box section of the spokes, and "pock" is basically the word spoke with the letters S and E removed. With the material distribution being relatively uniform and the inherent strength of the hollow, thin-walled cross-section, Wittenberg was able to achieve the uniform cooling and high strength required of locomotive drive wheels. The counterbalance was left largely hollow. However, the spokes were allowed to extend through the counterbalance to the wheel rim. The voids in the counterbalance were to be filled with lead to balance the wheel, and then a steel plug welded in place to seal off the void. The design of the boxpock also took into account the manufacturing process as well. The double disc construction required cores to be positioned inside the mold to create the hollows. The boxpock concept allowed for adequate support of the cores during the casting process and ease of removing the core sand after the wheel was removed from the mold. The Boxbach was manufactured by General Steel Castings of Granite City, Illinois, and was probably the most common of the four double-disc type drive wheels. The Union Pacific equipped their Big Boys, Challengers, and Northerns of the late 1930s with Boxbach drivers. However, the Boxbach wheel centers on these locomotives differed in appearance from the original concept. The opening between the spokes went from being wedge-shaped to being of a more elliptical form. Otherwise, the design and production methods remained largely unchanged. The Boxbach wheel centers generally fall into two categories. The Type A Boxbach is very close in appearance to the Scullin wheel center, a largely hollow construction with four large holes surrounding the wheel hub and two oval openings located on a line perpendicular to the center line of the axle and crankpin hubs. The Type B Boxbach is by far the most recognizable, since it's been featured on several famous locomotives. The Baldwin disc also evolved from its original design concept as well. Patented by Thomas Fawcett in 1933 and manufactured by the Baldwin Locomotive Works of Eddystone, Pennsylvania, the initial design incorporated hollow areas to reduce the weight and increase strength. However, the early Baldwin disc featured a flange between the cavity surrounding the hubs and the cavity supporting the wheel rim. The openings in the flange were round holes without reinforcing ribs. Like the Boxbach, hollow spokes extended through the counterbalance to support the wheel rim. The counterbalance itself was largely hollow and was intended to be filled with lead to fine-tune the balance. But unlike the Boxbach, the counterbalance featured a cover plate on its backside to seal off the void after the lead was installed. The version of the Baldwin disc that made it onto some famous locomotives, like the Pennsylvania Railroad's T1 and S1 duplex locomotives, was a bit of a departure from the original concept. The wheel centers on these locomotives made use of hollows around the hubs and wheel rim, and the spokes were also hollow. However, this version of the Baldwin disc featured reinforcing ribs on the spokes and teardrop-shaped openings flanking each spoke. Of all the wheel centers of this type, the Scullin is probably the most literal when it comes to the double-disc drive wheel. Invented by Harry Drebus in 1936 and produced by Scullin Steel of St. Louis, Missouri, the interior of the wheel is almost completely hollow, with radial reinforcing ribs placed strategically inside the hollow cavity. Three of the ribs extended through the counterbalance to the wheel rim. Additional support for the two wheel discs is provided by four large openings whose walls connect the inner disc with the outer disc. Fine-tuning the balance requires the use of lead in the counterbalance pockets and steel slugs welded into place to enclose the lead. Of the locomotives that employed the Scullin wheel center, the New York Central's Dreyfus Hudsons are by far the most famous. The reason for the New York Central selecting the Scullin may have been that the Dreyfus Hudson was a radical design and required an equally radical set of drive wheels. Whatever the case may be, the Scullin wheel centers definitely complement the looks of the Dreyfus Hudson. When it comes to the universal wheel centers, we really can't say anything about them that hasn't already been said about the other three wheel types, other than the universal was anything but universal. It's the rarest of the four and was most commonly used during rebuilds. There are instances where the Boxbach, Baldwin disc, and Scullin drivers were substituted for an existing wheel set while a locomotive received an overhaul. The wheel set most commonly replaced was the one carrying the main and side rods, but there are cases of other wheel sets being changed out as well. So there you have it, folks, our whirlwind tour of the fabulous four of double disc wheel centers. I hope you enjoyed the video. Please remember to like, share, and subscribe. And once again, my name's Steve, and thanks for watching. I'll see you next time.